Welcome to Study Loop.
So we have an RC circuit with a capacitor of 20 microfarads that's charged to 100 volts and connected to a resistor of 10 ohms. There's a switch up here, which is going to be closed at t equals 0. And then there's a smaller circuit over here, which has length A and height B, a distance C away from the big circuit. And the small circuit has a known resistance per meter and it has 25 turns. So what we want to figure out is what's the current in the big circuit at 200 microseconds, what's the current in the small circuit at 200 microseconds, what's the direction of the current in the small circuit, and why can we ignore the other wires other than this close one right here. So let's start by finding the current in the big circuit. So when the switch is closed, this is a discharging capacitor because there's no battery. So we can use the formula for a discharging capacitor, and the current is the battery voltage divided by R0. So this is the battery voltage, which is really the initial voltage on the capacitor, right? That's the actual voltage, times e to the minus t over the time constant, which is R naught times C. So now we can put in the numbers. So this is 100 volts over 10 ohms times E to the minus 10 ohms times 20 times 10 to the minus 6 farads. And that's all under 200 times 10 to the minus 6 seconds, right? It's a microsecond. And that is 3.7 amperes. So that's the current in the big circuit at the given time. So what about the current in the small circuit? So the current in the small circuit's a bit tricky. So first we should think about why there would even be a current. So the reason there'd be a current is because there's a current in this wire, clearly, and therefore it's making a magnetic field. So you have this wire and a small circuit like this. The current in this wire is down. Why is it down? Because current flows like that. It flows from the positive to the negative terminals. So the current is down, which means that there's a magnetic field in this small loop that's pointing out at us. So if you point your thumb or your right hand down and curl your fingers, you'll see that the current is coming out of the page like that. And that magnetic field is changing. So why is it changing? It's changing because the current is changing. The current in the big circuit, which is the thing that's actually making the magnetic field, is changing. So if the current's changing, the magnetic field's changing. And if the magnetic field is changing, there's a change in flux. And if there's a change in flux, there's a current because of Faraday's law. So the starting point for this problem is really Faraday's law. So E is N, the number of turns. That's going to be 25. That's N up there. Reduced EMF is the number of turns divided by the rate of change of the flux. So this sort of refers to another problem for calculating the flux, but we can sort of quickly do it here. So remember that the flux is that the definition of the magnetic flux is the integral of the magnetic field dotted into the area. So the magnetic field is the magnetic field of a long straight wire, which is mu naught I over 2 pi r. That's the magnetic field. And the area is the area of this square. So you're actually going to have a double integral, right? Because it's an area of mu naught I over 2 pi x dx dy. So X is from here to here. So X should go from C to C plus A. And Y should go from here to here. So 0 to B. And when you evaluate that integral, you find that it's mu naught I B over 2 pi times the ln of 1 plus A over C. So that was the result from another problem, but that's just kind of the summary. So let's now kind of use that fact. So we found, or we have, that the magnetic flux is mu naught I B over 2 pi times the ln of 1 plus A over C. So to be clear, this I that's the I in the big circuit. That's the thing that's changing in time. So actually di dt is going to be ddt of what we found in part A, right? What we found in part A was this expression for the current, right? That was what we saw in part A. So that's going to be just I over R0C, right? When I take the derivative, it brings down this factor from the t, but then what's left over is just I again. So that's why this I is still there. So using that fact, we have the induced EMF is N d phi dt, which is N mu naught B over 2 pi ln 1 plus A over C times di dt, right? So that's what we just calculated. So that's I over R0C. There's the induced EMF. And then we also have that from Ohm's law, the small current is the induced EMF divided by the resistance of the small current. So actually the final expression for the current in the small circuit is N mu naught B over 2 pi times the ln of 1 plus A over C times I over R naught C times 1 over R, where R is, so I'll actually label this R small, R small. How do I calculate R small? That's the resistance of the small circuit. Well, I know that there is 1.0 ohm per meter, right? We were given that there's the resistance of the small circuit is 1.0 ohms per meter. So I just need to multiply that by the length of the, basically the length of the wire. So how much wire is there? Well, there's 25 turns times the circumference of the square, and that's just 2a plus 2b. Right. So if you substitute in a and b, you'll find that this is 15 ohms. And now you know everything. So you know N, mu naught B, A, C, I, R0, and C. I'll just note that this is the same. This is the current from part A, right? So when you substitute all those numbers in, you find that I small is roughly 1.33 milliamps. So that's the magnitude of the current. Now, what about the direction? So let's go back here. So look, if you look at this diagram, what we established was that the magnetic field is coming out of the page at us. And is it increasing or decreasing? Well, it's decreasing because the current is decreasing, right? This is a discharging capacitor. So if it's decreasing, the induced magnetic field should also be pointing out at us. So the induced magnetic field, the induced magnetic field is also coming out at us. So if you point your thumb out of the page and curl your fingers, the right-hand rule tells you that the induced current has to be like this. So for C, it's actually counterclockwise. And then finally for D, why can we ignore? The question is basically, why can we ignore these other wires? And the answer is that the wire that's going to have the biggest contribution is by far going to be this wire, because if you look at the distances involved, this wire is much closer than this wire, right? This distance is 2 meters. So when you compare it to the size of this loop, which is only 10 centimeters, because this is so much further away, the effect of its magnetic field is going to be much smaller. And the effects of these two magnetic fields are going to be sort of equal and opposite. So that's why we don't have to worry about those. And that is the full solution to the problem.